How many trailing zeros are in 222 factorial? For this one, I have basically two different ways in mind. The first one will just do the normal method that I think is most commonly used for these kind of problems, and then we'll work on something a little different, alternative. But the normal method is something like this thing over here. The intuition on how this works, maybe think of something much smaller like 10 factorial. And when you expand it out, you're basically just counting the fives that are in this number. So expanded out, the only place where we have a 5 is going to be in here and also in 10, which is 5 times 2. Of course, we also need 2's. In order to get zeros, we need 10. But we don't even bother counting the 2's because there's always going to be more 2's than 5's, right? Because we have 2's all over the place. So we don't even worry about that. We just look for the number of 5's. So this kind of technique that you use on a small number like 10 factorial, you could do the same thing here. It's just that it gets tedious for large numbers. So what we do instead is use this thing over here. This is actually Legendre's formula in general, but what we're dealing with for the p is going to be 5. And we'll just kind of expand this out and do it. So this is going to be a sum of these terms with the floor function where the n is going to be 222. So what we're looking at here with n2 and p equal to 5, we get the floor function of 222 over 5 plus, and then we're just taking larger powers. The power gets incremented with this k value. So then we want 222 over 5 squared. This sum over here goes to infinity, but we don't need to keep going because what's going to happen is after a certain point, actually after this term right here, the floor function is going to take everything to 0 once 5 to the 4 is going to be greater than 222. So like if we write this term, it's just kind of pointless because this is just a 0. So all we need to do is add up these three terms, dividing 5 into 222. That's going to be, I think, 44, rounded down with the floor function. Then this one right here, divide 25 into that, you get 8. Again, rounding down. I mean, you get like 8 point something, but we round down with the floor and get an 8. Over here, that's 125 into this. That's just going to be a 1. Add that up, 44 plus 8 plus 1. And for the solution on it, we just get 53. So not too bad, not that much work. The method I'm going to show, the method I'm more interested in is going to be method number 2. Is it better? I have no idea. I just kind of like doing different things, but it's different anyway. But yeah, some people might just like to stay with the first method, but I think it's interesting. So to get to another formula for this, we'll start back again with Legendre's formula. Now what I didn't mention before is the left side of this equation. This notation over here is the p-adic valuation. I should write that out so you see what I'm saying. P-adic, like this, where in our case, we're interested in 5, so this would be like the 5-adic. I don't know if I'm pronouncing that right. So this would be the same thing for 5. So like when we, for our specific problem, we would write it like this. Now the way this works, like if we wanted to, I'll just show you like the evaluation, something like, I don't know, if we were dealing with base 3, 81 is the same thing as 3 to the 4th. And so this thing would just return the exponent, it just returns 4. And so we're dealing with this. Let's look at a couple different examples. Like, you know, it doesn't have to be positive. Like it could be, let's say if we have 1 over 125, where 125 is 5 cubed. So then this is, we could write it like this, 5 to the minus 3. And then this thing just returns minus 3. Now you also could have something like this, where there's no power of 5 in this. You could think of this like 7 times 5 to the 0. You don't even care about the 7 though. You just cared about the exponent on the 5. This thing would return a 0. Another thing you could have, let's do like one more at least, something like 50, where 50 can be broken up. We could write that as 2 times 5 squared. And then again, we don't care about the 2 for this, we just care about the exponent on the 5. So this thing is going to be a 2. So that's just a long way of saying what we just saw before is that we want to pull out all the factors of, in this case, 5, doing it in a factorial. That's exactly what we saw when we did 10 factorial. We were just pulling out all the factors of 5. So it's exactly what we want. Assuming, again, remember that we've got plenty of 2's in a factorial number, so we don't worry about that part. But what we were going to do is we just use this in order to find out how many 5's we have. But like I said before, I'm interested in doing it a different way, so I'm not going to use this exact formula as we already did that. What I want to do is take the number, in this case 222, and put it into base 5. So like for 222, I can write this as 1 times 5 cubed, because 5 cubed is 125. And then next we want powers of 2, 5 squared. That's going to be what, I think 3. That's going to get us 125 plus 75 is 200. And then just powers of 5 to the 1, that's going to be 4. So that gets us to 220 plus 2 times 5 to the 0. And so writing this in base 5, this is just totaling up these digits here. It's going to be 1, 3, 4, 2, base 5. Now, just doing this in general, this value is our n right here, the same n that's right there. We could write this as an expansion in terms of our prime number 5, our p value. So we could do it something like this. So then this right here represents the same expansion that we did as an example right here, but then just summarized concisely, put it in some notation over here. Now we're saying this whole thing's n, so all I want to do is take this and plug it back in for our n value right there. And so when we do that, we're going to need to divide in this p to the k term. And then because we're expanding that out as a sum, now we're going to have a double sum. So let's just see how that looks. And then now we've got that p value divided in, so we have our exponent looking like this. Notice that I dropped the floor because now everything's going to be an integer. In the cases when the exponent is negative, then what happens is the whole thing becomes 0. So we just drop the floor function and now we have this. But then here, let's just swap the order of the summations here. I'm going to kind of skip a couple steps just because I feel like it. And so we'll bring this sum to the outside, and then that's going to allow me to bring, this will become a constant with respect to this sum. So how it's going to look is now we're going from 1 to m. Here, we bring the a sub I out here, and then we'll have this sum over here. But then I can change this upper bound to I again, because what we saw before is it's not really infinite, because then we start getting a whole bunch of 0 terms. So once we get to I, that's going to be the last one, then everything else is going to be zeros. I probably should have changed it before, right? Because we were saying before it's zeros. Here you can't see it with the floor function gone. But anyway, what we have here, this is going to be a finite geometric series. So we can write that and use just the formula for that. There's a little manipulation that goes on. I'm not going to worry about it too much. But what we're going to have this sum out here. And then when we use the geometric series formula on this thing, we're going to get p to the I minus 1 over p minus 1 after a little manipulation after using the formula. And so let me take this, and we'll bring this to the top of the board and see if we can finish it. And then at this point, what we notice, p minus 1, that's just a constant in this series. So we can take this and bring it out front. We can have 1 over p minus 1, and then distribute this a sub I in. So maybe let's leave it in one sum. So we'll write it like this, and then we just have distributing in the minus 1 to this, we have something like this. And actually, let me break it up into two sums. So we'll break off this minus ai right here. But then what you'll notice, this first piece right here, remembering what these a sub i's are, this is when we did the base 5 expansion, like we wrote it out like this for 222. So then this is just the sum of all these coefficients like 1, 3, 4, 2, and all the different exponents of p. So then when you put this back together, this whole thing here, this is actually just n. And so we can take that out of the summation and we can just leave that as n. This right here is going to be the sum of the coefficients of the base 5 number. So we can use it just a notation, like just a shorthand on this, so we don't have to have a sum on it. And we can write this as the sum of the digits, base n, in our case 5, of just the number n. And sorry, the base should be p because that's going to be our 5. So we want this as base p. right here. And so we can take all this and put this together into a new formula. So for our p-adic valuation of a factorial number, we can just write it as n minus the sum of the digits of the base p expansion of it over p minus 1. And that's going to be our formula, and we'll just use that now to solve this problem here. So going ahead with the specifics, our p-value is going to be 5. So we want the 5-adic evaluation of 222 factorial, where n value is going to be 222. So we want 222 minus, that value is going to be the sum of the digits here. So it's going to be 1 plus 3 plus 4 plus 2. That's going to be 10. So we want 222 minus 10 over 5 minus 1, which is just 4. Reduce this, we end up with 212 divided by 4, do the division, and for the solution on it, we just get 53, and that's it. So there you go, 2 different ways to do it. I don't know which way is better. I kind of like doing, the nice thing with this is you can do the base 5 expansion, which I find pretty easy rather than dividing, but I mean, someone might rather divide, so I don't know. It's kind of the same thing. Anyway, that's it for today. Thanks everyone for watching. Have a good day.